Welcome. This is Greg Nordstrom, and we are now continuing in Weather Prediction 2. As I talked about in Weather Prediction 1, I kind of consider this one continuous class. So, again, we have now moved into Weather Prediction 2, and we're going to move into tropical forecasting. We'll spend the first really 2 units on tropical forecasting. We'll do kind of a tip series in about 4 parts. I'm going to do something in mesovortices and then also something on hurricane history. So that should be interesting and fun. And we'll, like I said, the first half of the class, we'll focus on that. Then we'll move into a good variety of things. We'll move into Western weather, long range forecasting, teleconnections, fire weather, different aspects of coastal weather. We'll do water spouts and lake sea breezes and rip currents. So we're going to have a good mix of everything. But again, we're going to start with tropical forecasting philosophy, so let's get right into it. That's how I feel about tropical forecasting. I love it all. As I've told you before, I'm a bandwagon of weather. I love it all. But tropics are my favorite. I just have always been fascinated by them. And with chasing these amazing storms, while tornadoes are incredible and I love snow and, I really enjoy all different aspects of weather, being in a hurricane is just a whole different beast. It's a whole different experience. It's really something hard to really explain in words without you actually being in it and understanding how these things work. It's just an incredible thing. Now, of course, just like anything in weather, there's a lot of sad and bad things with it. But strictly from a meteorological standpoint, like for example with Hurricane Charlie, being 150 mile per hour category 4 and watching the winds just ripping things to pieces and then go to calm almost in a couple minutes was one of the most amazing things I've ever seen. So hurricanes are definitely my favorite. So we're going to spend some time on it. All right, so here's the first part. This is part one of the tips. I got 4 parts of that, and again, mesovortices as another lecture, and also a lecture on hurricane history, which I think you guys will enjoy. Kind of share some of my research and different things I've done on old historical famous hurricanes. So we're going to go break these down lecture by lecture. And, one thing with these tips, and I tell this to everyone, you can't use everything at once, right? I'm going to show as many tips as I know. I'm going to try to teach you as many tricks as I can. I don't know everything, obviously, but I'm going to show you as much as I can. And hopefully, as a forecaster, you're going to find the tips and tricks that you enjoy most, all right? So it's really up to you to pick the ones that you find work the best for you. Because just like I was talking about in Weather Prediction 1, forecasting really is an art. And no two people are going to do it exactly the same. But this is just some tips that I've learned over the years. And I've been very blessed. I've had some amazing teachers. And I've been very close to some very famous storm chasers. Jim Leonard, who was really the pioneer of hurricane chasing. He's the first person to ever hurricane chase, and he was doing it back in the 70s and 80s when no one was doing it. And, it took a lot of skill, and this guy really was ahead of his time. And he taught me a lot. I learned a lot from my good friend Michael Laka. Like I said, I follow the history. So I've been blessed. I've just immersed myself around a lot of great people that show me some cool things when it comes to hurricanes. All right, so let's start with the basics. Triggers for development. And when I talk about triggers, I'm not talking about 80-degree water, no wind shear, stuff like that. I'm talking about the mechanism behind it. All right, so you got easterly waves. Where do these originate from? Well, you get these clusters of thunderstorms that move off Africa, and as they move across the Atlantic Ocean, a lot of these waves will develop. Not all of them, but the majority, especially of stronger hurricanes, develop from these easterly waves. You can also get hurricanes from stalled fronts. Especially as you get later in the season, you'll get these fronts that are moving down through the United States and pushing into the Gulf of Mexico or Caribbean or off the eastern U.S. And sometimes these stalled fronts can develop. A very famous example of that was in 1983 with Hurricane Alicia. You had a stalled front that moved through the Gulf of Mexico and eventually developed into a tropical cyclone that eventually became a Category 3 hurricane that hit Galveston, all right? So that's one of the more famous examples of that. You can get them from upper level lows. So what is an upper level low? Well, all an upper level low is just a pocket of cold air aloft, right? Well, yeah, obviously you're dealing with tropical weather, right? So you're dealing with warm core, not cold core. But with time, this cold core, if it sits over this warm tropical waters with, an atmosphere that's conducive for development, it can evolve, and over time, it will evolve into a tropical cyclone. It can happen, all right? Not very common, but it's something that does happen, all right? Also, upper level lows will really influence how these develop sometimes. That could be the fly in the ointment. A lot of these upper level lows are not easily seen, especially 3, 4, 5 days out. Sometimes they can ventilate a storm, and sometimes they can rip and shear the storm apart. All right, and then especially for the Atlantic, one of the more rare ways is something they call a monsoon trough from the ITCZ. This is incredibly common in the Pacific, but in the Atlantic, pretty rare. If you do get one of these, you have the ITCZ, where what do you have along that? Enhanced convection, you have convergence of air, and sometimes a piece of energy can break off that ITCZ and move a little bit, gain some latitude, and eventually develop into a tropical cyclone. Again, much more prevalent, very common in the Pacific, and not very common in the Atlantic. Watch for tropical development in a post-amplified pattern. So what do I mean by that? Well, if you have a big trough, like we were just talking about with stall front that's sitting over the Gulf or sitting over the eastern U.S. or into the Atlantic, and you have, thunderstorms and some, upward motion, and that trough moves out and leaves a little piece of energy behind, and then now that high builds in over the top and it becomes more favorable for development, sometimes those fronts or pieces of energy left behind can become tropical, all right? So that's something that you want to look for in a post-amplified pattern. And then another thing that you need to be careful about, I see people kind of jump the gun a little bit. They see a blow of convection and they go, oh my goodness, it's going to go tropical. This is something we need to watch. And then 12 hours later, it's gone. So convection needs to persist for at least 24 to 48 hours to really start to evolve into a tropical system. Just be careful there. I've seen people get tricked a little bit with that. I like to see it for at least minimum 24 hours, but really close to the 48 hours. All right, so this goes back to the, easterly waves here. While only about 60% of Atlantic tropical storms and minor hurricanes, Cat 1s and 2s, originate from easterly waves, nearly 85% of the intense or major hurricanes, Cat 3 or above, have their origins as easterly waves. And this comes from Lancey and his research in 1993. If you want to learn a lot more about hurricanes, this is the guy to look up. He has so much amazing research on hurricanes. He flies on missions around the hurricanes, and observes the atmosphere around it to try to help the modeling. This guy is an awesome guy. I've met him a couple of times. Very nice man. So if you want to look up some more stuff, just type in Lancey and hurricanes, and you'll find some cool stuff. It is also suggested, though, that nearly all the tropical cyclones that occur in the eastern Pacific Ocean can be also traced back to Africa. All right. So, again, most of the major hurricanes, where are they coming from? Easterly waves. All right, so now we're getting into our first real tip here, and I've seen this many times. I've experienced this as well. An intensifying hurricane at landfall will cause more damage than a weakening storm at the same intensity. So you got two storms at 150 miles an hour. It makes a difference whether it's strengthening or whether it's weakening. Now, what's the reason for that? Well, it's more readily going to be able to mix stronger winds aloft to the surface, leading to more widespread verification of maximum wind speeds. Well, if you're strengthening storm, what's happening? These updrafts are much more efficient, and you're pulling those winds aloft back down to the surface. Whereas if you have a weakening storm, these updrafts are not going to be as efficient. They're weakening everything, the whole system. It's, the engine is slowing down, right? So while, yes, you can still pull some of those faster winds aloft to the surface, it's not going to happen as readily as a intensifying hurricane, okay? So a great example of this was Hurricane Katrina before it got to Mississippi. When it was going over South Florida, it was only a Cat 1, and my family was down there at the time, and I know a lot of people down there, and, a lot of people, especially in Florida, Cat 1, they're not overly concerned, which not really a good thing to have that mindset, because we know even a tropical storm can cause incredible amounts of flooding and damage. But, in general down there, Cat 1, people are not overly worried. Well, this one surprised people. Even though it was only 80-mile-an-hour winds, it was strengthening as it was moving towards Florida and over Florida, and it got the full 80 mile an hour effect. All right. So in that situation, when you have a stronger, intensifying, well, not necessarily stronger, an intensifying hurricane, you're going to get that full force of what it's giving you. So in that example with Katrina at 80 mile an hour winds, you saw tons of areas across South Florida with sustained winds near 80 miles an hour with gusts much higher. Whereas Hurricane Lily, for example, which is the first hurricane I ever chased, at one point Hurricane Lily was a Category 4 in the Gulf of Mexico, but it started to rapidly weaken as it moved inland. And as it moved towards the shore and made landfall as it was weakening rapidly, even though it was 90 mile an hour at landfall and it was actually technically a stronger hurricane landfall than Katrina over South Florida, you saw far less observations of higher wind speeds with Lily. Why? Well, a lot of times with the weakening storms, when they come in, you might get one or two observations of 90 mile an hour winds with gusts pretty close to it, all right? Whereas with Katrina, you saw 80 mile an hour wind reports all over the place with much higher gusts, all right? Your gust ratio is going to be much higher in an intensifying hurricane. And think about that, right? Like, what is a hurricane force wind? Well, it's a 1 minute sustained wind. Well, if you have 80 mile an hour winds, what's the likelihood of your 1 minute sustained wind just being 80 miles an hour for a minute straight? That doesn't happen, right? It goes up to 90, goes down to 70, goes up maybe to 95, so it's going up and down, up and down. Well, with these intensifying hurricanes, where you're efficiently mixing those higher winds aloft to the surface, you're getting higher gust ratios as well, which can kind of bump up that, sustained wind as well, all right? So again, bottom line, intensifying hurricane makes a big difference. Now, if you're talking a weakening 140 versus a strengthening 80, okay, that's a whole different story. But when they're getting close to the same strength, when you got, 100 versus 105 or 110 versus even 120, if there was a 110 mile an hour hurricane coming in that was intensifying versus a 120 mile an hour hurricane that was weakening rapidly, I'd be much more concerned about the 110 mile an hour hurricane coming in that's intensifying rapidly, all right? It makes a big difference. So again, Katrina, we talked about that. And while I was in Gulfport when Katrina hit, and it was absolutely catastrophic. I mean, the storm surge was 28 feet, one of the worst things I've ever seen in my life. Thankfully, it was going through an eye wall replacement. And as it came into, the border of Louisiana, Mississippi, and obviously the right side here along the Mississippi coast was absolutely obliterated with the storm surge, it was weakening. And even though it was still a very strong hurricane, at 125 mile per hour winds, and it's not like the winds were weak by any means, but you didn't see it overachieve on the wind side, all right? Obviously, the winds were still bad, but thankfully it was weakening, was coming in. If it would have came in a day earlier and was strengthening, I can't even fathom how bad that would have been. Hurricane Lily, opposite. It peaked in the Gulf, and then it really started to weaken. And this is the first hurricane I ever chased, so to me it was still an amazing experience, and I've never seen anything like it at that point. But looking back on it now, it's kind of funny to think about that, that it was, Cat 4, and, thankfully, obviously, that it weakened, because if it would have kept its strength, it would have been big problems all through Louisiana. But, it's funny to think from my standpoint that I thought it was so amazing because I've never been in a hurricane. And then now that I've been in 18 hurricanes, looking back on it, I'm like, oh, wait, that actually really was nothing. All right. So, again, all storms are dangerous. Tropical storms can cause problems. Look at Allison, for example. Look at Harvey. Yeah, Harvey was a Cat 4 when it hit Texas, but what was the real story behind it? Was the flooding, especially in Houston, right? So, again, even when they weaken, they can still cause a lot of problems. But again, big difference between weakening and strengthening when it comes to the wind. So major hurricanes, ones that have a well-defined inner core that moves across land, often do not regain their intensity once back over water, while weaker storms can max intensify rapidly once back over water, assuming there's no dry air or shear. We'll explain this in a little bit more detail here, all right? The land disrupts the inner core of the hurricane, causing it to weaken, while a lot of times these outer bands are still mostly over water or close to the water, and they continue to have healthy convection, preventing the inflow from getting back to the center or the surface of the storm once back over water. So to really keep this simple, it's kind of like the skater with the arms out and then pulling it in, right? The more I'm pulling that in, When you go to things like going back to angular momentum and things like that, I'm pulling this in, I'm tightening my circulation, I'm going to be a stronger hurricane, right? If I take those arms out, yes, the energy may be distributed over a larger area. You may affect in a larger area. You probably will, but the actual max intensity goes down, right? So it's not easy to get a major hurricane, all right? The atmosphere needs to be near perfect to get major hurricanes. They're not overly common. It doesn't happen every year all the time, okay? And when it is near perfect, and when you do have a major hurricane, and you have this well-defined inner core, if that core gets disrupted, it's very hard for it to just get its act together right away, okay? It will eventually, as it moves back over open water, start to kind of come back together, but a lot of times it doesn't have time, especially when you're dealing with the Gulf of Mexico or when you're getting to the Caribbean or you're getting closer to the United States. And I'll show you some examples of that with Isidore and Gustav. So the bottom line is these are exceptionally amazing things, right? Amazing storms. This is like a Ferrari engine or a Lamborghini or a sports car, right? And as awesome as those engines are, and as amazing as they are, sometimes the littlest things can mess it up. And that's really what's going on here with these major hurricanes. You have this perfect engine, basically, this perfect, almost perfect core, that if it gets disrupted, it's not going to just come back together really quick. And what happens, too, is when it gets disrupted, the skater's arm starts to open up, the core starts to expand out, right? And a lot of times as the core expands out and these bands are over open water, they stay strong, but these inner bands never really get their act back together. So while the energy spread out and it may affect more areas, that pure strength has been distributed, has been moved over a larger area, and it's hard for it to tighten back up, all right? So hopefully that makes sense. Isidore, right? I remember this well. It was forecast to come through the Gulf and cause havoc. Well, a couple things, and we'll talk about this later. Frictional effects helped pull it in a little bit here in the Yucatan, but it got pulled in, and it was sitting just in, over land, and a lot of these bands were over shore. Well, it's a Category 4 hurricane as it was coming, near the Gulf of Mexico, a very strong hurricane. Well, it sat over land, so obviously, hurricanes over land, it's not going to strengthen, and the skater opened its arms up. But a lot of those bands were still over water. So those bands over water still stayed pretty healthy, but the core was disrupted. The core was kind of broken to pieces, right? So eventually it popped back over in the water. I remember a lot of people were forecasting, Cat 2 again before it made landfall. And there is some argument maybe it did get back to a minimal Cat 1. But officially, it never did get back to a Category 1 hurricane. It popped over the water, and it did start to try to organize itself, but because that core was so perfect, it just never was able to get its act back together, okay? If that hurricane would have been weaker, if that would have only been a tropical storm and maybe a minimal Cat 1 and it didn't have that inner core and it got disrupted, then it would have moved back over water and it had a much better chance for that core to redevelop, all right? So again, the land disrupts the inner core of the hurricane, causing it to weaken, while the outer bands over water continue to have healthy convection, preventing inflow from getting to the center of the storm once back over water. But on the flip side, if you have a weaker storm, you have a tropical storm, you have maybe a Cat 1 storm, and the core gets disrupted, the core was never this perfect engine. It was more like my 1998 Camry, right? It's efficient, it works well, it's going to get you where you need to go, but it's not a Ferrari, it's not a Lamborghini, right? So the storm's over land, and it's more of a tropical storm or a Cat 1, and it gets disrupted, but when it moves back over water, it's not like those outer bounds were really strong. It was all pretty uniform. So when it gets back over water, that one has a better shot at tidying up. So if Isidore would have been a tropical storm or a Cat 1, I think actually as it came back to land, it probably would have got up to a Cat 2, maybe even a Cat 3, all right? Remember Michael? Now, obviously, Michael's an extreme example, but you saw how fast that thing went. I mean, it went from tropical storm to a Cat 5 pretty quick. And I'm going to show you examples where this is not something that doesn't ever happen, all right? Not saying it would have got to that, but my point is if it would not have had that well-defined inner core, it would have likely strengthened much more efficiently and faster and would actually have been stronger on its landfall here in Louisiana. But that's not what happened. It had a really nice, well-defined inner core. It got disrupted. The outer bands over water stayed strong. The skater's arm moved out. That air was never able to get to the pure center of it again. As it went back over the water, it was trying to tighten up, but it just ran out of time. Okay. Another example of this was Gustav. All right. It's not like the western coast of Cuba is like huge mountains. Now the eastern coast, different story. This is more of the tobacco area here, in the western area. But still, it was almost a Cat 5. All right, so that's as perfect as it gets. I mean, Cat 5s are not major hurricanes not common. Cat 5s is really not very common. So even this little bit of land disrupted the circulation enough that core opened up and it was never able to tighten back off when it went back to Louisiana. I chased the storm. I remember it well. I remember the forecasts were for at least a major hurricane, if not a Cat 4 for this area. Well, thankfully for the United States, it clipped Cuba. The circulation got disrupted, and it wasn't able to really tighten back up in time. Now, it's still a significant hurricane. It was still a Category 2 hurricane. It's not like it was not strong at all. But if it didn't clip the tip, if it would have gone more in the middle there, it probably would have been a stronger storm, all right? Now, with Charlie, when it came through here, it was just weak enough that even though when it clipped it, it didn't really have that perfect defined core, and it really got going here, right? So if Gustav again would have been maybe a Cat 1 or a tropical storm, then yes, it would have been disrupted, but it would have been able to regain its intensity as it went back over the water. All right, frictional effects versus desire to remain over open water. I really saw this with Hurricane Charlie, all right? Now, obviously, did Hurricane Charlie just turn right because of the frictional effects of Florida? No. There was a massive trough digging through the Gulf, which turned Charlie to the right. But the frictional effects did have enough of an influence to make the difference from the landfall being more Tampa versus 50 to 100 miles south. While, yes, it was horrendous where I was in Port Charlotte and Punta Gorda, Tampa was fine, all right, because it was a small, compact storm, all right? So with Charlie, it turned to the right partially due to frictional effects, Isidore as well. This is more likely with faster storms, and that's what Charlie was, a faster moving storm. I believe is moving around 20 miles an hour or so. And it's really similar to moving over one tire on the shoulder. Let's say you're driving on the freeway and you're going pretty fast, going 70, 80 miles an hour, and you're not paying attention or you drift off a little bit and the car kind of moves over to the right. What happens is you go into that shoulder area there. You feel that pull, that little brief pull to the right. It's not like you get pulled and you go completely off the road, but you feel a little bit of that pull to the right, right? That's the best way I can kind of explain this. It's being turned to the right because of the trough, but that frictional effect helps just kind of pull it just a little bit more to the right. So this played a big effect with Charlie. I remember a lot of people were forecasting and saying it was going to hit Tampa. And we were actually just north of Tampa when that day started. Well, because I knew this tip already, and I was watching the radar and I was watching the observations and I saw that little fade there, I was like, all right, we got to go south of Tampa. Now, obviously, there's luck involved. To get in the eye of a 5 nautical mile wide hurricane, I don't care how much skill you have, there's always luck. But I used this tip to at least go, you know what, I'm going to stay in Tampa. I'm going to go a little bit more south. Because it's more pronounced on Florida. The way Florida is shaped as a peninsula, the littlest, 1-2 degree shift can lead to hundreds of miles of coastline. Let's say, let's go back to a hurricane what's a famous one? Floyd, right? Remember Floyd in the late 90s, I believe it was 99, and it was coming towards Florida, and it was a tricky forecast because as it was going to the Bahamas, a 50 to 100 mile difference where it turns here could be the difference between Florida and North Carolina or completely missing the coast. So even though it's not a huge pull, these little pulls can make a big difference on where it goes along the Florida coast, right? Slower storms are less likely to feel this effect, same thing kind of with a smaller storm as well. So when they're faster and smaller, they're more likely to feel it. Best way I can describe it is if you're in, let's say again, my 98 Camry, or you're in a Geo Metro, a small car, and you're going 80 miles an hour, and you touch the side of the freeway there, you're going to feel that pull to the right, right? But if I'm an 18-wheeler and I'm going 20 miles an hour and I pull to the right, do you think I'm really going to feel anything? No, I'm an 18-wheeler and I'm not going very fast, right? So this is more of an effect with a faster storm and a smaller compact storm, all right? And that's exactly what Charlie was, all right? Short-term influence, it's not something that's going to continue. It's going to go back on its normal path, but it could lead to a big track difference, especially with the coastal shape of Florida. Again, I talked about that with Charlie and Tampa. Again, from a meteorological side, that was the best day of my life. I mean, to see what I saw was incredible. But of course, the damage and what it did was not great to see. Like I've talked about in Weather Prediction 1, I mean, Katrina haunted me for a long time. For months, I thought about that storm and dreamed about it. And now that my fiance is down here in the Mississippi Gulf Coast and I spend so much time down here, it's almost like a second home to me. You can still, to this day, see the scars of Katrina all along the Mississippi coast. It is coming back. It is really coming back strong, but you can still see plenty of scars of Katrina even today. All right, so storms that make landfall perpendicular to the coast may see an increase in the wind speeds as frictional effects may tighten the pressure gradient. All right, you saw this with Harvey. You can see this with a lot of storms that are coming in, especially a faster moving storm. All right, so it's more of a factor with higher terrain, and it's also even more pronounced with faster moving storms. So how do we break this down? All right, let's say you have a faster moving storm heading towards the northern Gulf Coast. It's not really being interacted with sheer dry air at this point, and it's a strong, healthy 125-mile-per-hour hurricane. Well, the hurricane hitting at a perpendicular angle, as it comes in, the frictional effects as the storm comes, it's going to kind of tighten it a little bit, and it's going to increase that pressure gradient. A lot of times you'll see the eye trying to come in the shore there, and it almost like it becomes a little elliptical because it's like trying to avoid to go in because obviously it wants to stay over the warmer water, right? And it kind of like jumps in. You kind of see that jump. Well, a lot of times right along the coast with these perpendicular hits, you'll see a little ramp up of the pressure gradient and a little ramp up of the wind, all right? This is more pronounced if you had a mountainous area, right? If you had a faster moving storm that was moving into an area where you had mountains, well, think about it. Is the storm just at the surface? No, these thunderstorms are going tens and tens of thousands of feet in the air. So if you have a mountain range that's 10,000 feet, and a storm is moving perpendicular and hits that mountain range, it causes a compressional effect, not just at the surface where the friction of the trees and the sand and the beach area is. You get compression as you go up, higher in elevation, right? So hopefully that makes sense. It just compresses the storm. It gives you a little bit of increase in that pressure gradient. And again, you're going to see this more in faster moving, especially more pronounced with higher terrain, okay? And this assumes that the storm is not weakening for other reasons, okay? So, this leads into this, and it leads into a misconception a lot of people think with the 38 hurricane, all right? So the northeast quadrant is typically strongest wind and surge. Now, when I say typically, we're learning more and more and more. There's a lot of micro and mesoscale stuff going on. But keeping this basic, the northeast quadrant is typically, because why? I mean, especially it depends on where you are, but let's say I'm making landfall on the northern Gulf Coast. What's that northeast quadrant coming in? I'm not getting the frictional effects along the southwestern side that's already come across the land. I'm coming over the open water, and that's where your strongest winds and surge typically is, all right? But this is not because you can add the forward speed to the wind speed. Will a faster forward speed at a perpendicular angle cause everything to tighten up and get a little bit of a jump in that pressure gradient and cause your winds to go up a little bit? Yes, it will. But is it as simple as saying, oh, the hurricane's 100 miles an hour and it's moving 60 miles an hour, so I just add it to the winds? No, it doesn't work that way. Physics just doesn't go that way, because think of it this way. If you're going to do that and you add 60 mile an hour on one side, then you have to subtract 60 miles an hour on the left side. So you're telling me it's 160 mile an hour winds on the right side and 40 mile an hour winds on the left side? No, that's not what's happening, all right? And that's a misconception. The key is the storm structure and the circulation of land versus water, all right? Is the flow coming off the open water, or is it coming across friction and land? Makes a difference, all right? Left, north side, and then we're talking, Gulf Coast, along the eastern coast of the U.S., we're talking United States here, will be influenced by mid-latitude features and shear before the right south side. And again, be careful with these microscale features and mesovortices. Great example would be Andrew, right? Yes, you're taught, and typically it's true that if a hurricane was coming towards Miami, that northern eye wall would have experienced definitely the highest surge and some of the highest winds because that's the air coming off the off the water with no friction, and that's where all the water is going to be piled up. But you look at Andrew, and some of the fastest winds were to more on the western or even southwestern side, as you had these mesovortices spinning around the eye, right? And sometimes within these mesovortices, you get a huge increase in wind. This is actually one of the last things that Fujita studied, and we're going to spend a good amount of time talking about this in lecture 3. All right, so again, the 1938 Long Island Express. First off, if you haven't read about this storm, go read about it. There's some awesome books. I can go through my book list and I can post some of those on the discussion board. I have a lot of cool hurricane books that I've bought over the years. This hurricane, I believe, did hit a 5. It was either a strong 4 or in the 5 range, and it just accelerated up the coast. Can you imagine today a Category 5 hurricane that's somewhere in the Bahamas and it's moving at 60 or 70 miles up the coast heading towards New York City? You imagine the panic, and what would you do? What do? You can't really evacuate that many people that fast, right? You just tell people to go to a stronger area. And this area of the country does get hit by hurricanes. They've been very blessed and lucky. I'll show you some examples where they've been hit in the past. But the big misconception with this storm, even though it was an incredible storm, one of the strongest storms that ever hit Long Island or just New England in general, is you read a lot of people or a lot of books, especially from back in the day, where they talk about, hey, the hurricane's 120 mile an hour and it's moving 60, so the winds are 180. Well, yes, there was a wind gust at 187 miles per hour in the Blue Hill Observatory in Massachusetts, but there is some elevation with that. Keep that in mind. That's not right at sea level there. But still, 187 mile an hour wind gusts anywhere in New England, that's incredible. Unless you're in Mount Washington. Okay, that happens there. Actually, more than you would think, or at least close to that type of winds. But, closer to the shore, this was just an absolutely devastating hurricane. I believe Providence was under like 15 feet of water, incredible wind gusts, high winds. But the key with this is it's the storm structure, right? That's why this quadrant here was the worst. And it was coming at a perpendicular angle. And what do you have here? You have a lot more what around here? Mountains, right? So that helps compress it a little bit. But again, it's not as simple as adding the wind speed. That's just not accurate. I don't know if you have Jamie Dreyer for any of the classes. I'm sure you do. I'm sure you have him in some of the classes, or at least have seen him in lecture. I always talk about this with him. If you want to get into a great discussion with him on why that's not accurate, definitely hit him up because he would love to talk about it. But still, yes, the forward speed does cause the pressure gradient to increase a little bit, and it does help the winds maximize a little bit. But is it as simple as adding the winds to the forward motion? No, because it's not like it was 180 mile an hour winds here and, 40, 50 mile an hour winds here. The winds were still very powerful on this side as well, okay? So that's just a misconception I see a lot of people do. So just be careful with that. Going to when I was talking about with New England, look at the 54 season. You had Carol and Edna. I believe they were both Category 3 hurricanes that, went through Connecticut and Massachusetts here. There's a famous photo, I believe it's from Carol, of one of the, not exactly sure what it is, if it's like a country club or a marine harbor or something like that that's being destroyed. But these were brutal hurricanes. You imagine today if you had 2 major hurricanes within a month or weeks actually coming into New England, people would be just beside themselves, right? Plus, while yes, even in 1954, there was a lot of people living in New England and New York, but it's not like now, all right? It's not like 2019, okay? There's a lot more people living there. There's a lot more infrastructure. There's a lot more homes. There's a lot more businesses. There's a lot more things in the way for these storms to destroy. If you had 2 back-to-back major hurricanes in New England, it would be devastating. And it's going to happen again. We've been very blessed and lucky. Go back even further. You can read, I believe it's 1821, they got crushed by a hurricane. You can go back even further in time, to when the settlers first came. There's been hurricanes for a long time that's affected this area, and some big, strong ones, okay? You also have, what is this one here? Hazel. Hazel was flying as it was coming up. And I believe the winds in National Airport or in Washington, D.C. was pushing 90 miles an hour. 90 miles an hour, okay? So that's pretty significant. So this was a bad season. And, New England's been blessed, and fingers crossed, I hope they stay blessed. But eventually their luck's going to run out. Here's an example also from the 50s. You can see, Edna in 54, Carol in 54. What's this one? Donna. I mean, Donna was just a beast. Went through the Keys, and it went through, the Outer Banks here, and then it went up into New England. But look at all these storms. You have Connie and, Hazel and Gracie, and then you had a lot of storms, all right? And look at where a lot of these storms were focused in the 50s into early 60s, right? That's my point. We've been lucky, all right? But this area does get hit, all right? Even though it hasn't maybe happened in my lifetime or maybe many other people's lifetimes, if you were born in the 20s and 30s and you grew up through World War II in the 50s, you saw plenty of hurricanes up there. All right, so as a tropical cyclone approaches the coastline, sometimes, not always, especially a weaker storm, a tropical storm, it may jump back over the ocean, okay? And I'll explain this in more detail. And it's not like it's literally jumping, but the center is not well defined, and sometimes the center will redevelop to the south or redevelop to the north, and that can play havoc on your track forecasting, all right? So jumping across islands like Cuba, Hispaniola are very important with long-term track, right? Let's say you had a hurricane that was supposed to move north of Hispaniola in Cuba and go through like the Florida Keys or South Florida, but it was really weak. And it kind of gets, affected by Hispaniola that has huge mountains. And, the center never really is strong. It's kind of bouncing around because the center is not always a fixed point. It's moving around a lot. So the center sometimes will go, you know what? Boom, I redeveloped south of Hispaniola. And now that track forecast goes from going through the Florida Keys, and now I'm looking at the Gulf. It's going to head more towards Louisiana and Texas, all right? Or you can have the opposite. It's going to go south of Hispaniola. Looks like Texas, Louisiana. It's not an organized storm. It's really weak. The center jumps north of Hispaniola. Now you're looking at the Keys, right? So that's just something you got to be careful on, something to really focus on, especially with the track. Could be the difference from a Florida landfall or a Central Gulf Coast landfall. Models will struggle with this because you don't have a well-defined center. If you had a well-defined hurricane, you don't really need to worry about this. This is more pronounced with weaker, slower-moving storms. The center sometimes relocates or redevelops, okay? The model has a hard enough time seeing the center as it is, but if it's jumping around, it's just making it even more difficult. So be aware of that. I've been burned on that before, all right? Isaac was an example of that. A lot of the initial forecasts were very different, but the center kind of jumped to the north, and then the forecast was adjusted. I believe it was Ike. Even though Ike was more well pronounced, but there's been other storms where they've jumped across. Like, hey, you got a storm that's moving this way. You think it's going to continue and go this way. Well, the center is weak. It jumps north, and now it's going more this way, or the opposite. Center is moving this way. It's really weak. It starts feeling the influence of the mountains here, and then it jumps to the south, and now it's going to go more this way. All right, so it's just something to watch. It can cause some problems with your forecasting. All right, so question. Is a slow-moving storm more likely to maintain strength on the Gulf side of Florida or the Atlantic side? So think about the storm structure, okay? All right, and we'll get to that here. And also, carefully monitor storms that manage to survive hostile conditions that are still intact when they reach more favorable conditions, all right? So those are two thoughts I want you to kind of think about, and then we'll talk about that, all right? So this is one of the most famous hurricanes in recorded history, all right? In my opinion, this is the king of all hurricanes, 892 millibars in the Florida Keys. If you want to read some amazing books, they have one called Category 5, another one called Storm of the Century by Willie Dyer. Incredible story, and I'll talk more about this when we get into hurricane history. But the answer to the first question here is the slow-moving storm is more likely to maintain strength on the Atlantic side, not the Gulf side. But why? All right, so if I'm this slow-moving hurricane, which this was the 35 hurricane, it's fairly slow-moving, Well, it went from basically a tropical storm to a Cat 5 in about, I don't know, 24 to 30 hours. I think it went from like 85 to 185 in about 24 hours. All right. So an incredibly rapidly deepening storm. But as fast as it was deepening, it almost weakened just as fast. It went from the strongest hurricane in recorded history in the United States to a weakening Cat 1 by the time it got to Cedar Key, right? So why? Well, first off, slow moving storm here on the western coast of Florida. While yes, it's not like Florida is, dry, especially compared to like, I don't know, the Great Plains or off on the west coast, but still it's a lot drier here than it is over the open Atlantic, right? So if a hurricane was moving on the eastern side of Florida, you're not going to get this drier entrainment as much, okay? You're going to have that flow coming in over the open water. You can still get some drier from here, but in general, you won't get the same drier entrainment that you would get in this scenario here. Also, what's happening that's even more important, it's slow moving, right? So that's going to cause upwelling as it is, but you're getting this. What kind of flow are you getting off of? You're getting this easterly flow coming off of Florida. What does that do? Well, that pushes that warmer water away from the coast and causes upwelling. All right, so you're getting entrainment of drier air. Slower moving storm is naturally going to have upwelling of cold water anyway, but that easterly flow just enhances it even more, and you get nice upwelling, entrainment of dry air, and a lot of times, especially when they're close. Now, I'm not talking about out here. I'm talking close to the coast. You're going to see rapid weakening, whereas if it was turning on the east coast of Florida, you wouldn't see near the same type of weakening. You would still get weakening with the interaction with the land, but you don't get that dry air coming in as much, and you're not getting near as much upwelling as well. All right, and look 35. Cat 5 to Cat 1 pretty quickly there. When we talked about surviving hostile conditions, it's not like these storms have personalities, all right? They're not people, okay? But it's weird how these things work. I remember Andrew, I was 12. It's not like I was old or anything, but I do remember it well. This is one of Hugo was really the first one I followed closely. But Andrew, I remember a lot of the forecasts were for it to go out to sea. Well, it was feeling the tut and it was getting pulled, and there was an upper level low, I believe, out there, and it was just getting sheared to pieces. And a lot of the initial forecasts were for it to either die in this very hostile environment or get pulled out to see what was left of it. All right. A lot of times, what happens, you see the lower level, and mid-level centers decapitate, split, and one will go in one direction, one will continue the other way, and it's dead at that point. Right. So that's what was a lot of the forecast for Andrew. Well, that's not what happened. It survived that hostile condition. Now, it barely survived, but it survived. And then that ridge started to build back in, and it went from a hostile condition to a favorable condition, and Andrew just went ballistic, all right? So something I've noticed over the years, again, it's not like they have personalities, but if you see a hurricane in hostile conditions that really should die, and it doesn't die, and now the conditions are becoming favorable, look out. That's just something I've noticed over the years. Andrew's a great example of that. Is it always going to happen that way? No. None of these tips, nothing in weather is always going to happen exactly. I'm just trying to find, cool little tricks just to help you give yourself a little bit of an advantage, right? Nothing's 100%. Like I told you at the beginning, if you're getting 2 out of 3 right, you're pretty darn good forecaster, right? One of the best, really, okay? It's just hard. It's not easy. But I'll tell you this, if I saw a storm that I really thought should have died and it was in a very hostile environment, and then a ridge started building in and became a favorable environment with very warm water and no dry air, I would be very concerned. All right, and Andrew is a great example of that. All right, so again, nothing's perfect, but when we're talking 9 out of 10, I'll take 90% all day long in forecasting, all right? Like I said, in Weather Prediction 1, you're really, when we were winning national titles, it wasn't because we're getting everything right. It's because we're less wrong than everyone else. Really, that's your goal. Be less wrong than your competitor, all right? Or, the other, team you're forecasting against, all right? So 9 out of 10 tropical cyclones that develop east of 35 west longitude recurve harmlessly out to sea. 9 out of 10, not all of them. The ones that don't are usually really bad, but still, 9 out of 10 is pretty good. A faster a tropical system develops, the more likely it is to be influenced by the weakness in the ridge that is often found in central Atlantic, the tut, tropical upper tropospheric trough. Okay, it's kind of hard to pronounce, but that's what it is. It's not always present, but a lot of times it's present there. And when these storms intensify, what happens? The cloud tops are getting higher, you have higher updrafts, everything's expanding. You're going to feel the upper level more, and if I'm strengthening and expanding faster, I feel the upper levels and I move out to sea. Whereas if I stay weak, I stay weak, I stay weak, I don't really feel that upper feature and I can kind of slip underneath, all right? So a faster tropical system develops, again, the more likely it's to be influenced by the weakness in the ridge found in the central Atlantic. Weaker storms are steered by lower level winds, while stronger storms are influenced more by mid and upper level winds, okay? And the majority of tropical cyclones that make U.S. landfall develop 5 days or less before landfall. Camille, Michael, Katrina, most of these big 35 Labor Day, most of these are developing pretty close to the U.S. Why? Well, if I'm closer to the U.S., I have more chance just statistically to hit the U.S. There's less stuff in my way, or there's less things in my way for either to get curved out to sea or hit and get destroyed, or other factors, right? The further out I am, the more the gauntlet I have to get through to get to the U.S., right? Larger systems that come off Africa are more likely to develop in smaller systems. Another little tip I've noticed, you have a huge gyre of energy. A lot of times that will, even in more rough conditions, colder water, wind shear, and dry air, can survive and then move into more of a better conditions and develop. Whereas if you had a really small, weak easterly wave, it's probably going to get eaten up or destroyed more easily, okay? So a great example of this was the 2010 Atlantic hurricane season. 19 named storms and not one hurricane made landfall in the United States. 19 named storms is tied for third most active from a name standpoint, right? So it's a significant season in terms of the names. But what I always tell people, what's worse? 19, 20, 30 storms, but none make landfall, or 3 or 4 storms with a Cat 3 or 4 that hits, or 5 that hits. Of course, the one that hits. It only takes one to make it a bad season. Andrew is a great example of that, 1992. One big hit, and it was Andrew, right? 35, even though there was another Yankee, they call it the Yankee hurricane that came from Bermuda and came back down towards Miami later on, which actually influenced the 35 hurricane survivors that came up to Miami, a whole nother story we'll get into later. But that was a pretty low number season. I believe it was 7 storms, somewhere around there. And the 35 Labor Day was a Cat 5, so it made it a bad season. Well, look at this season. 19 named storms, no landfall in hurricanes, and what I believe was going on is these waters were so warm, and that's why it was accurately predicted that we're going to see a lot of names. That part was predicted well, but the landfall part didn't work out, really because they got going too quick. They were all forming so fast that they felt this weakness. I believe it, I can't remember which one it was that got really close. I think it was Earl. I believe Earl was the closest one that came, and you did have some near hurricane conditions, off Cape Hatteras. But in general, look at all these storms that developed quickly. They felt the tut, and they were taken out to sea, right? So a lot of times when the water's too warm and the conditions are too warm and these systems get going too quick, a lot of times that's good news for the United States, and they move out to sea. Where I get more concerned is when these areas is not as good, but it gets better as you get closer to the U.S., that's actually where I get more concerned. Because you have something that's weak, it slides under the tut, starts getting better conditions, and then starts to explode as you're getting within that 5-day range of the U.S., all right? But a lot of times when they develop quickly, they go out to sea, okay? However, when they don't, this is that 1 out of 10, and this is the recent one, Irma, right? So you have that look like it's going to gain in latitude. Well, there really wasn't a tut. There was a strong ridge here. So actually it bended back off to the south and even south and west. You ever see a hurricane in this part of the Atlantic start to bend back to the southwest? That is bad. That is not good. Okay, that's that 1 out of 10. All right. What's another famous hurricane that's that 1 out of 10? The 1928 Lake Okeechobee storm. That was a long track one that formed well east of 35 West. So again, 90% is pretty darn good, and that tip is money. I think it's one of the best tips there is. But when they do make it, that 1 out of 10, they're usually pretty bad. So just keep that in mind. All right, it's not 100%. All right, so typically the region between Hispaniola and South America is hostile to intensification until late in the tropical season. This is due to divergence resulting from thermal lows over adjacent land masses. Best chance for intensification is if the storm is moving at less than 18 knots. If storms are moving too quick, you can get them decapitating themselves. You remember when I was talking about the lower level and the mid level split in part? If a hurricane is moving too quick, it's basically forming its own shear, and it can kind of, decapitate itself or choke itself off. All right, so you don't really want hurricanes going much higher than 18 knots. You want them less than 18 knots, and of course you want them gaining latitude away from South America, right? If it's just hugging along South America, it's also getting sheared and affected by the landmass. All right, so I'm going to explain in more detail why it's more hostile early in the season, but keep in mind you really want them moving less than 18 knots and gaining latitude as well. All right, so Harvey is a great example of this. All right, it died basically, and then redeveloped when it got back here in the Gulf, and then it just went bonkers. It was a great environment, and this is a great example where we have incredibly improved when it comes to track forecasting, but we still have a long ways to go in intensity forecasting. Not to go too much of a tangent here, I did feel confident it would redevelop, and I remember telling my class at Mississippi State that I felt strong that it would redevelop and become a hurricane, and maybe even a Cat 2. And at this point, when it was completely ripped apart, that was a pretty aggressive forecast. But did I see Cat 4? No way. I don't think anyone at this point saw Cat 4 here. All right, so again, we have a long ways to go in intensity, but focusing on that tip, what's going on early in the season? Okay, so early on in the season, not that the water is cold, but it's colder than the land masses, right? So you have higher pressure, surface high pressure over the water, and these land masses are much warmer early on, right? So you get low pressure over like Hispaniola and over South America. So what happens in the low levels? The air is diverging, right? You got high over the water, low, low, so high to low, right? So what's happening? Those winds are spreading apart. Do you want divergence in the surface for a hurricane to intensify? No, you want air converging, coming together, right? So early on in the season, this is a hostile area, and it ripped Harvey up. It basically killed it. But enough of it survived that when it got back in a more favorable environment, remember going back to Andrew, great example, where it probably should have died and it didn't, and all of a sudden it's in a more favorable environment and it just went crazy. It was just enough of it was able to survive, and then it just went absolutely bonkers. And obviously, it was the rainfall that was the big story. But if you're in Rockport, if you're in these places here in Texas, you experience Category 4 conditions, which is not common, all right? That's fairly rare. That was the first Category 4 since Charlie. Not quite as strong as Charlie, but still a very strong hurricane. Well, what happens later in the season? Well, now this water's really cooking, really warming up. Some of the water here is some of the warmest you're going to see. But now, as we get later in the season, the land starts to cool off a little bit, but the water still stays warm. So now you got low pressure over the water, high pressure over the land to the north and to the south. And now what's happening as you get later in the season? High to low, and now you're getting air piling up and converging. So later in the season, this goes from more of an unfavorable place to a more favorable place. Basically, you switch the circulation. Early on, you're getting more divergence. Later on the season, you're getting more convergence. Okay, so I hope that makes sense. Shear will typically weaken a storm, but watch for evidence that departing shear is actually ventilating the storm. That goes back to the upper-low thing I was talking about. Florence was a great example of that. While Florence was still a devastating hurricane as far as flooding, it was forecast to be much stronger as it came in. Well, there was some sort of upper level feature that was shearing it, and it's a fine line. If that upper level feature is far enough away, it will ventilate the storm. It will help the outflow of the storm or the exhaust of the storm really get going, right? And help the air flow into it more. Whereas if it's too close, it will kind of choke it off. It will kind of shear it. Sometimes, and they call these outflow jets, that where these upper level features are in the right position, they can cause these outflow jets to really ventilate the storm and strengthen it. But again, there's a fine line. Sometimes these upper level lows are too close, and they actually shear and they hurt the storm. Okay, so that's something that's tricky, and only really there's no real way to forecast this in the longer term. It's more of a shorter term, near term type thing. All right, so it's something you got to look for. And studies have shown that hurricanes are 4 times more likely in the Gulf of Mexico and Western Caribbean during the rising phase of the Madden-Julian oscillation than during the opposite phase. I'll talk about this in even more detail, but when you're in more favorable phases or octants in the Madden-Julian or the MJO, you have more you have more convergence, you have more rising motion, and studies have shown that you're 4 times more likely in the Gulf of Mexico and Western Caribbean to get development. That does not mean you can't get hurricanes when you're not in favorable phases. You can. It's just when you're in a favorable phase, it enhances it. It's 4 times more likely, all right? Now, 4 times more likely doesn't guarantee anything. But again, we're playing the odds here. 4 times is more likely is better than no times more likely. This is crazy to me because I've been talking about this for 20 years, and it's still still a problem, all right? The GFS has a tendency to underestimate the strength of the subtropical ridge or break it down too quickly, especially when SSTs are warmer than normal, okay? So the GFS, while they're trying to improve it and they're doing lots of things to improve it, and I'm sure with time this will get better, it still struggles big time with this, okay? Especially when the sea surface temperatures are running above normal. Well, what's been happening in the Atlantic the last, really since the mid-90s for the most part, not every year, but the waters have been running pretty above normal, right? So you have a model that struggles already enough with heat as it is. It usually underestimates the strength of the ridge, not with just hurricanes, but with nor'easters and other weather features. Do you know how many times in the GFS I would see nor'easters on day 3, 4, 5 always going out to sea, and by the time you get inside day 3, you start seeing them hitting New England? The GFS has always had this right bias, and it's really pronounced with hurricanes as well. And again, especially when the water is above normal. If I have a problem identifying heat, and it's in an area with a strong subtropical ridge because a lot of heat, and there's even more heat than there normally is, the model that already struggles with it is really going to struggle with this, all right? So as a result, it has a tendency to recurve storms out to sea too quickly. It did this with Ivan. It did this with Katrina. Not always out to sea, but it just has a right bias. Francis. Irma recently. You remember initially where it was coming more towards, the eastern part of Florida or just missing Florida, and then it went to the western part of Florida? Well, I mean, it already has that problem, and now you got this warmer water, so the ridge is even stronger than what the model thinks. Plus, what was Irma? Irma was a Category 5, and these strong storms will add a lot of heat to the ridge, all right? And, what's happening in these strong storms, you're emitting a ton of latent heat, and that's just going to pump the ridge or influence the ridge. Like, it's just going to cause the ridge to balloon out even more and more and more. And the more that ridge balloons out, it's not curving to the right and going out to sea. It's going more and more west, all right? So that's something I've seen for 20 years now, not just with hurricanes, but also with nor'easters. Be wary of that. I even with Isaac, I saw that. It was supposed to hit South Florida, went further south, and it went more towards Louisiana, all right? But be aware that a bias does not mean that model will always make the same mistake, okay? It's not like the GFS always makes this mistake. Most of the time it does. If I had to put a percentages, I would say at least 2 to 3. I say 2 out of 3 times at least, and maybe sometimes up to 3 out of 4 times, all right? But it's not always going to do that, all right? Just like any model, you see people sometimes like, oh, the NAM's always wrong. Well, yeah, maybe the NAM's struggling, but it's not always wrong. Sometimes it's right. So even though the GFS has this bias, and it's something I see over and over and over for 20 years, it doesn't mean it's always going to happen. So you do got to be careful about that, all right? Don't get too confident or too cocky with this because sometimes, you'll get something will slap you back and take you back more to being humbled, right? That's just part of forecasting. But this tip does work really well. All right, so let's look at Katrina, right? I remember looking at this, and again, the hurricane center just gets better and better and better and better, just like everyone else. We're all improving, right? And I've noticed, especially over the years, they went from following the GFS more closely to looking more and hearing more about the European and other global models, right? As we advance as a science and we have more tools, we start using these tools and we get better. But back then, not that 2005 was way, it was almost 15 years ago. But I remember this very well. I remember looking at the ridge of Katrina and what was happening at this point. The forecast and the GFS was showing it going straight across Florida and then coming more towards the panhandle here. Well, if you remember Katrina, what did it do? It started diving southwest, and it did more this and then this. Well, why was it diving southwest? Because the ridge was stronger than what the GFS and the models thought, right? So again, it thought it was a weaker ridge. Well, you had real warm water and a stronger ridge on a model that already struggles with this problem. So it just enhanced that problem even more. And Katrina dove more to the southwest. The ridge was stronger. It ballooned out more. And then what happened as it got here? You just had a strengthening storm that's adding latent heat. And it caused the air to be more over towards, Louisiana, Mississippi versus, more Panama City. Okay. So I remember this well, and you saw as each day went, the track kept shifting west. And then when we got within that 24 to 48 hour range, it was pretty obvious what was going to happen. Okay. But a little bit further out, when you're in day 5 or 6, GFS is going to struggle with this. All right. It's something I've seen over and over and over. All right. A couple more tips here. Models and forecasting. The tropical models use GFS input for handling mid-latitude features. Global models can be used to forecast the track of the tropical cyclone, but not the intensity. So, it's getting better. It's improving. The resolution, both vertically and horizontally, it's just getting better and better and better and better. I mean, I look at the 13-kilometer Euro all the time, and that's a global model. I mean, that's incredible, right? But while it's getting better and better and better, we still have a ways to go, okay? And one thing to keep in mind is with the H-Warp or the H-Mon, this used to be the GFDL. These are currently the two primary products that have the potential to forecast track and intensity within reason and within theory, right? So they're using a nested grid model, right? So they're using a smaller domain, right? If I'm a global model, I'm using a massive domain. So how detailed can I really get? So in theory, if you have a nested grid and you have a smaller domain, you should be able to get more detailed and figure out more of the smaller things with the hurricane. Like, is the shear going to affect it? Is the warm water going to affect it more? Are we going to have eyewall replacement? Are we going to, have more of a rapidly intensifying storm? In theory, it should work that way, right? But what's the problem? All that outside stuff is still being filled in with the GFS, right? So if the GFS has a right bias, it doesn't mean that the H1 and H-Warp is going to have as bad of a right bias, but it's probably going to take on some of the characteristics that the GFS has as a bias, right? All right, so again, we've gotten better with track forecasting. We've gotten really good with that, all right? We're not perfect. We're gotten better. Intensity forecasting still got a long ways to go. H-Mon and H-Warp in general, these higher resolution models should do better in theory, but that's not always the case. But be careful. All that outside stuff is being filled in by the GFS. So if the GFS has the right bias, even though the H1 and the H-Warp may not have as much of a right bias as GFS, it's going to take on some of those same biases, all right? Because that whole outside area is being filled in with the GFS, all right? So again, intensity forecasts are still poor overall. Charlie recently, 35 Labor Day. How about Hurricane Michael? I mean, we knew it would be intensifying storm, but who saw Cat 5, right? Harvey. Recently we've had plenty of examples of storms, even, in 2019, 2018, that we did fairly well with the track, but not so great with the intensity because it's difficult. It's hard, all right? Remember, this is a fine-tuned engine, so the littlest thing can mess it up. Or, if everything's perfect, they can just go, right? Like when it gets that, it's like pushing that ball down the hill. Once it gets going, it can really get going. So 35 Labor Day, great example. Obviously, in 1935, you don't have near the capabilities we have today. And again, we'll talk about this storm in more detail. But if you want to read some cool books, Storm of the Century by Willie Dyer is the one I really recommend. 85 mile per hour to 185 in 24 hours. Hit the Florida Keys, 892 millibars. I mean, just absolutely incredible. 185 might actually be a little bit on the low end. It could have been, gusts were definitely well over 200, easily. All right, so this is what we're going to end with here. The upper air pattern over eastern Asia can provide clues, hints on the upper air pattern over the eastern U.S. 6 to 10 days later, especially when major amplification is involved, all right? So let me read through it and I'll explain in more detail. It's especially helpful when a typhoon is involved, as that will pump the ridge. Remember, if you had a strong storm, it releases what? A lot of latent heat, so that can do what? It can cause the ridge to expand. And a lot of times when you pump the ridge, you then downstream cause the trough to be stronger and then downstream. So it causes a downstream effect, okay? This cannot be used to forecast development, only track. And we're going to focus more like Tokyo to Cape Hatteras, but you can really look at the southeastern part of Asia and kind of put that in the southeastern part of the U.S. into the Gulf of Mexico, okay? But we're going to focus on Cape Hatteras to Tokyo, both about 35, 36 north latitude. So what's the best way to explain this? Let's say you're in my class and someone was sitting in the back of the class and I told them, take this rope and hold on to it. So I give someone a rope in their back of class. If I take that rope and I yank on it, you're going to feel that downstream effect in the back of the class, right? The harder I yank on it, the more you're going to feel it, right? So that's kind of how you have to feel, or how you kind of have to look at this. And I'll be honest, when I first heard this, I was like, really? Seriously? Something that's happening over, Tokyo is going to give me a hint in the U.S.? Well, that's when I was first starting to learn. And then I started looking at it and really practicing with it and going like, wow, this actually works really well. Now, is it perfect? No. There's a 6 to 10 day range, okay? It depends on the wavelengths. You have shorter wavelengths, you have longer wavelengths. This is more towards the beginning of the season, later the season. That's where experience comes. You're going to have to fine tune it a little bit here. But if I see a huge trough over Japan, right? And I see a hurricane curbing off the, Japan coast, right? When I see that, or not hurricane, I say typhoon curbing off the Japan coast. When I see that, I think to myself, okay, you got this big trough that's over Japan. It's causing the hurricane, because usually when troughs dig in about 10, 15 degrees in front of the trough, what happens? Hurricanes curve out or typhoons curve out. Sometimes, rarely, they'll merge into it, but most of the time they're curving out. Trough digs in, push and help curve that storm, either hurricane or typhoon out. But if I see a big trough over Japan and I'm seeing the GFS or the Euro or any model show a big ridge over the U.S. in 6 to 10 days, I'm kind of hesitant of that, all right? So why is that important? Well, this is going to help me with this longer-term forecasting, okay? If I was looking at the GFS at day 9 and it's showing a hurricane barreling through, I don't know, North Florida or South Carolina or, through Wilmington or something like that, but I see a massive trough over Japan and a typhoon recurving out that's just going to amplify that even more as it moves across the globe, because how are these things moving? They're Rossby waves, right? It's not like you got a trough in Japan that just keeps going all the way across the globe, right? You get a ridge that influences the trough, that influences the ridge, that influences the trough. It's a downstream effect, right? Okay, and these Rossby waves change throughout the year, okay? They're not always the same number, right? The wavelengths change. But to keep this as simple as I can, if I see a big trough over Japan, and I see a hurricane curving out to sea, and I see the GFS and the Euro showing a hurricane barreling into the southeast U.S. in 6 to 10 days, I'm really hesitant on that, okay? Now, on the flip side, if I saw a big ridge over Japan, and I saw a typhoon that just barreled right through Japan or through Southeast Asia, and I looked 6 to 10 days later, and I saw the GFS and the European showing a hurricane barreling through Florida, I feel a lot better about that, because I know the pattern over Japan is matching up to what the pattern over the eastern U.S. is. And again, Cape Hatteras and Tokyo are the two areas that really line up well, and then from there you kind of move off to the south and west, and you can kind of line up the southeast U.S. and the Gulf of Mexico, all right? Again, you may think, really, man, are you serious? I promise you, practice with it. Again, nothing works perfectly, but this works great, not just with hurricanes. Now, again, if you have a typhoon that's barreling in Japan, does that mean a hurricane is going to hit the U.S. in 6 to 10 days? No, this has nothing to do with development. It's only going to help you if a hurricane is developing and coming, all right? So if a typhoon is barreling in Japan 6 to 10 days later, it could mean nothing. But if a hurricane was coming 6 to 10 days later, it's probably going to continue towards the U.S. Whereas if you have a big trough over Japan, then probably any hurricane that does develop, if it develops, if it was coming to the U.S., would curve out to sea 6 to 10 days later, all right? So that's basically what you're really looking at here. If you have more questions with that, you can always email me or talk amongst yourselves on the discussion board. Of course, I'll chime in, but again, it works well, and it's not just for this. It's also temperature forecasting. Down the road, you can. If I see a big trough in Japan and I see the models forecasting a big ridge in heat, I'm going to be hesitant towards that, okay? There's a lot of teleconnections, and we'll talk more about that when we get into the second half of the class. But this is a good one when you're looking at hurricanes. And again, it's not for forecasting development. It's only if you have one. This will help you with the track. All right, so, here's kind of hard to see. Here's Japan. You got a trough digging in here. You see that trough really digging in. So if I saw that trough digging in and I saw the GFS show a hurricane barreling right towards North Carolina, now obviously this is hour 186, so you better be sure this is correct. And then you got to add 6 to 10 days from this point, so you're starting to get pretty far out. But let's just pretend this was hour 24, right? Or this was current. If I saw a big trough through Japan and I saw the GFS 6 to 10 days out showing a massive hurricane barreling right through South Carolina, I'd be a little hesitant. Whereas if I saw the GFS and the European showing a big hurricane curving out to sea, I'd feel more confident about that, all right? So that's how you use it. But one thing to be careful about that I learned my lesson on is you also got to look at the pattern to the east of it. I'm really focusing on Japan and through Southeast Asia because I'm looking at, here's Tokyo, more to Hatteras, and then this would be more the Southeast U.S. into the Gulf of Mexico. But what happens out here is important as well. There's a couple times I just boxed myself into that area and I didn't look at a trough to the east. So, let's say in this example, it was showing a big ridge, right? And I was just focusing on this area. But just to the east of Japan, there was a big trough. Well, that could still grab the storm and pull it out. So all I'm trying to say is, yes, this is the area you want to focus on, but be a little careful. You still want to look off to the east and see what's going on here as well. If you see a big ridge here but a massive trough here, that's something you're going to want to consider downstream. All right. All right, actually, this is the last thing that kind of leads into this, all right? And then we'll move on to part 2, all right? So strong highs over New England and eastern Canada support a lowering of pressure over the tropical regions to the south, which could lead to tropical development when the pattern persists, okay? So the best way for me to explain this is to show you this, all right? If I see ridging, mid-Atlantic, northeast U.S., this part of Canada, Ontario here, I start to get concerned in the longer range, right? So you got this high, and what happens? You got that clockwise flow around the high here, right? But what do you have in this area? You have trades coming from the east. So if I have this clockwise flow around the high and the trades are coming from the east, what happens? Air starts to collide and it starts to pile up. So you start getting more piling of air and rising motion. So a lot of times where this ridge axis is to the south, you need to look for development. Does it always happen? No, because you can have a lot of dry air, you can have a lot of shear. But if your conditions are favorable and you don't have dry air and you don't have shear, and I see a ridge that's persisting, I'm not talking a ridge for a day. I'm talking a ridge persisting for like a week. You start having ridges that are persisting for like a week or more, I'll tell you this. Sometimes the models will pick up on it, but even if it doesn't, I know this is the area to watch. Let's say I saw this big ridge in the northeast U.S. It was a really strong, powerful ridge up in the northeast U.S., and I was looking at day 7, 8, 9, 10, and it was not showing anything here. I don't care. I know because this ridge is here, and especially if there's not dry air and shear, something is likely to develop to the south of it, right? Joe Bastardi always calls it the ridge over troubled waters, right? You got this big ridge, and then you have trouble to the south, all right? That's why he kind of calls it that. In this example, it did show some development, nothing special, but, it gives you the idea that's the area to the south that you'd want to look for development, okay? Here's another example. Ignore this because this did not verify. But you see that stout ridge, right? So where would you want to look for lowering the pressure? Down in here, right? So if this persists over time and you start seeing the model showing a lowering of pressure, even if it doesn't show development, that makes sense, right? You got that ridge. You got that flow opposing the trades, causing piling of air. You got warm or hot water, deep warm water, no shear, a lot of moisture, no dry air, and then look out. Again, ridge over troubled water, right? And then, here's more of an ensemble look. So obviously ensemble, to show something that pronounced in a week, is pretty significant. Now as you go through time, it won't be as pronounced, but you see that ridge is just sitting there, right? Ridge just sits there, sits there, sits there, right? If I saw that, I would be worried about the development side. And you can kind of see that you can kind of see that weird little kinking to the lines here and stuff. So even though it's not really showing a lot of lowering pressure because it's an ensemble, right? It's 51 members, right? Maybe half are showing something and half are not, right? That's why you got to be careful with these ensembles. But still, if I see this type of agreement of a ridge, I'm looking to the south, and this is the area that I'm looking for development, okay? All right. So this is a good place to start with part one. Part one will probably be the longest one. It's the most information and the one that I can really break it down in detail. I know it was a lot, but hopefully you found this useful. Even if you're not in the area that is going to forecast tropics, you never know where you're going to end up. Or, when you do see these things go on, at least you can follow along and kind of have an idea what's going on. If you do live in tropical areas, again, maybe you're not going to use every single tip, but use some of them and start practicing with them and see how they work. Nothing's perfect, but it'll give you an advantage, okay? All right, well, I hope everyone again enjoyed this, and I'll be back shortly with part two.